Hi everybody, I think we're going to do a little sample problem here working with buffers. My plan is to show how you would figure out how to make a pH 3.5 buffer that is 200 millimolar with its ionic strength. I'm going to use HF and F minus as my conjugate pair here, and I've written down, just because we're going to need it later, the pKa of HF. So I think what we're going to do in this problem is I'm going to show you how to figure out what's going on with this buffer and how to do the calculation. And then I'm going to loop back around and I'm going to do a more traditional ice table afterwards and show you why we can make some approximations that we tend to make when we're working with buffers. So, all right. First here, what I'm going to do is I'm going to write down the acid reaction for HF. And so that's going to be HF plus a fresh water is in equilibrium with F minus plus H3O plus. Okay, this is my reaction that I have here. I can see my conjugate pair is here and here. And so what I want to do is I want to make a buffer. I'm going to use the Henderson-Hasselbalch equation, which is pH is equal to pKa plus log of AHA. All right. The first thing I'm going to do is I need to just do a little math here so that I can figure out the ratio that's associated with these two things here. So I'm going to put in what I know. I know I want a pH of 3.5. That's going to be equal to 3.14. That's the pK. Remember, I had that before. Plus the log of this ratio here. So that ratio, if you do the math on this, that thing, which I just have listed as a question mark above, that is going to be 2.29 is the ratio. So that's a little bit of a rounded number there. So that tells me how much of this conjugate base that I need relative to the acid form, which is great, but it doesn't yet incorporate anything about the ionic strength. So the ionic strength is going to be what you get when you add those two concentrations together, and we're going to get 0.2 molar. I'm just doing a conversion there from the 200 millimolar. So now I have two equations. Here's one and then the second equation and two unknowns. So I just need to go through the process of solving this. I'm going to take the HA and multiply it up over here, and then I'm going to substitute that quantity in for right here. So it's going to be 2.29 HA plus HA is equal to 0.2. I'm just going to drop the units there to make that a little bit cleaner and easier to see. All right, so this is going to collapse into 3.29 is equal to 0.2. So that's 3.29 HA is equal to 0.2. So that's some pretty easy math to do there. And I have it written to the side over here. So HA is equal to 0.061 molar. And now that I know that, I'm going to plug this number in probably up into this one, though of course I could also go up here. And let's solve for that. And I would find that A minus is going to be equal to 0.139 molar. So nice check, make sure that these do indeed add together to equal my ionic strength, which is up here. And also I have this correct ratio that's sitting there. So if I were to make this acid, for example, one way that I could end up making this acid is I could use the chemicals. So you'll see that I have, this is some generic terminology down here, but then I have my HF up here. I'll switch back to that. So let's say that I'm working with HF and I'm also working with KOH as a strong base. And I want to be able to make this particular buffer. So one way that I could kind of talk about this, and let's see how this goes for us here. I'm going to rewrite this so that I can make a little bit of an ice table, except that I'm going to do this differently. I'm going to say, here's HF plus my KOH, though I really want people to get rid of that K, because that's going to be a spectator, and I want you to just think about it as the OH minus. This time, this is my acid, this is a strong base. This is going to be a very potent single arrow that goes over and is going to produce F minus plus a water, because we're going to take this proton over here and neutralize with that. Okay, so if I use an ice table here, what I'm doing is not our traditional ice table where I'm about to do an equilibrium row with the equilibrium constant. This is going to be a limiting reactant problem here. I am going to say that this is the initial, that's the change, and this time it's the end amount. And I have the end amounts sitting right here. So I'm going to go ahead and put those in. So this one right here, I need this to be 0.139. This end amount, so I'm in molarity here, hopefully that's evident. This one I'm going to put in right here, 0.061. Okay, I have another piece of information where I know that my ionic strength has, both of these have the A minus. This one just happens to be protonated. But basically, this is how much of the actual chemical do I have is that ionic strength. And I am only able to get any fluoride into this solution by putting it in through the HF here. So I cannot put any of this OH minus in if I'm trying to get any fluoride in, just simply because it doesn't have any F minus in the chemical here. So what I'm going to do is I'm going to completely load all of the F minus that needs to be in there, which is going to be 0.2 molar, by putting in this chemical, 0.2. All right, so now what I'm going to need to do is I'm going to also need to put in this, which is going to convert some of that into this species over here. Now, the only way this is going to work is this has to be a lesser amount than that. So I can't convert all of it over, or I've taken myself out of the buffer zone. I'm not starting with either of these here. Okay. And what's going to happen, and maybe this is a bit of a logic puzzle, is we'll see that I actually need to load in the same quantity here that I'm going to end with of my base. And it's because, again, this is the limiting reactant problem. So I am going to react all of this away. Okay, so 0.139. Notice that my math ends up working out nicely for me here. All of this goes away, so now I have none of that remaining. This is going to be a plus 0.139 and another plus 0.139 over here. Though I'm not particularly worried about it, this is going to carry down. I've made a little additional water. So what I can see here is I need to put in this quantity, these are in molarity, of both of these things initially here. And when I do that, this one-way arrow limiting reactant problem, I will convert some of the HF over to F minus, and I'll do this with the correct proportions so that I'm going to get the right ratio up here for that Henderson-Hasselbalch that I eventually needed.